Unit circle, sine and cosine functions. Mathematicians figure out that if we work using a unit circle, which is just a circle with radius 1, as you can see here, then it is simpler to write out the formulas. And not only that, it will provide us with a lot of tools for us to summarize all the facts, all the results that we have gotten. You will see. You may say, Professor, how come the unit circle simplifies things? Could you show an example? Well, notice, right? If you use among all infinitely many circles, a circle with radius 1, notice that if you apply the formulas that I mentioned before, right? Being this x comma y, the coordinates of point on the terminal side of an angle theta, then notice that if this is a unit circle, then this guy should be 1, 0. This guy should be 0, 1. This guy should be negative 1, 0. This guy should be 0, negative 1, right? But most importantly, we can say that sine, which was defined as y over r, since the radius is 1, look how it gets simplified. Y over 1, y. Sine of theta equal y. Cosine of theta under our general definition was x over r, right? But r is 1. So 1 into x, x. So here you can see quickly that sine is equal to y and cosine is equal to x. So I can say that the first coordinate will give me sort of for free cosine of theta, and the second coordinate will give me for free sine of theta, right? So first simplification, first useful tool that we're gonna use, right? First coordinate will be cosine, second coordinate sine if you use the unit circle. Now tangent will be just the quotient of sine over cosine, y over x, right? So y over x. Okay, great. So now notice that now if you remember this formula for the arc length, remember I gave you a formula for the arc length. S, the arc length, can be measured via this formula, r times theta, right? R times theta. But since we are working with a unit circle, r is 1 times theta, I end up with this simplified version of the formula. S equal theta, S equal theta. Aha. What does it mean? It means that in the unit circle, S, the arc length, right? This arc length, and the angle numerically are the same, which allows me to set up a one-to-one correspondence between the angle and the length of this arc. So the length of this arc, if you call it T, and the angle are in a one-to-one relationship, right? So this suggested something for the mathematicians. If the arc length you represented with T, right? Not with S, but with T. See here, right? T. Then it means that T, some real number, right, can be paired up in a one-to-one way with the angle. So just like you talk about trigonometric functions of theta, you could talk about trigonometric functions of real numbers, right? Because this T could be any real number, it's a length, right? So that's something really good. In what sense, Professor, is good? Well, because now I can talk about trigonometric functions of real numbers. Sine of the real number T should be equal to the sine of the angle theta, the unique angle that is associated to the real number t, right? In radians, of course. But that is computed here, is y, right? Y. Sine theta, y. Cosine of a real number t should be the same as cosine of theta, but cosine of theta in the unit circle we are saying is x, right? So x. And tangent of the real number t should be computed as sine over cosine y over x, right? There you go. I have the three trigonometric functions of a real number t, right? And you may say, where are the other trigonometric functions? Well, the others, you can get them by flipping these three, right? So the others can be gotten by taking the reciprocals of those three trigonometric functions. Now, this is a big deal because it will allow me to do, for example, some graphing of trigonometric functions, right? Because now t represents a real number, right? We will be able to do graphs of sine, cosine, and tangent on the XY coordinate system, right? Oh, that will come next on the next lecture, right? But for now, let me kind of show you how you take advantage of this unit circle. Well, first, let me show you this first example. I will do number one, you will do number two. On number one, they're saying, right? The figure shows an angle in a standard position with its terminal side intersecting the unit circle. Very good information here, the unit circle. Intersecting the unit circle. Evaluate sine of theta and cosine of theta. Well, we just explained that if you are working in the unit circle, the first coordinate x is cosine, right, of the angle. And the second coordinate y is sine of the angle, right? That is if you work in the unit circle, which is the case, right? The unit circle is one. So then quickly you say, right? Sine of theta and cosine of theta can be gotten from the unit circle directly. How? Cosine is the first coordinate, minus 5 over 13. You just pick it up, right? And sine is 12 over 13. Done, right? No computations are needed. So then you just look through and you will see that then this should be the answer, right? Sine of theta 12 over 13, cosine of theta minus 5 over 13, right? And all this because we're working in a unit circle. Can you try to do in the same way this one, number two? The hint, remember, first coordinate is cosine, second coordinate is sine, right? Which one do you think should be the answer for this problem? Mm-hmm. Yeah, let me give you a hint. First coordinate x, this is second coordinate y. The first coordinate is always associated with cosine in the unit circle. The second coordinate is associated with sine, right? Mm-hmm. You may say, Professor, but it's a negative angle. Doesn't matter. This property will always hold for unit circles, okay? Always will hold for unit circles. Okay, guys, look, let's do it together then, and then we can move on. While looking at the unit circle, then I can say that cosine of the angle theta, right, should be the first coordinate, 7 over 25, and sine of the angle theta should be the second coordinate, minus 24 over 25, right? So therefore, if you look through the choices, the one that is stating this is a choice D, right? Mm-hmm. Follow, guys? Great. Now, there are some other exercises here, such as this. They deal with negative angles, positive angles. So let me show you how, using the unit circle, it's easy to compute this type of things. For example, sine of minus 180, cosecant of 270, right? Sine of 270. Let's start with this one. For example, suppose they ask you to compute sine of 270. 270 doesn't fall into any quadrant, really. It's between two quadrants, right? They are called quadrantal angles, this here, right? But however, remember, if you work in the unit circle, right, then this point should be 0, minus 1, right? This point, 270 degrees in the unit circle. But remember, in the unit circle, the first coordinate cosine, the second coordinate sine, right? So I pay attention to the second coordinate, so I can say that sine of 270 degrees will be just -1. Follow, guys? Helps, right? Yeah. Another one here, maybe you can try this one. Yeah, this one. Can you try this one, the first one, number 3? Sine of minus 180 degrees. I'm gonna do the diagram for you to figure it out. On the unit circle, we're talking about this point, right? This one, negative 180 degrees goes like this. There. And the coordinates are minus 1,0, right? So recall that the first coordinate in the unit circle give you cosine, the second coordinate give you sine, right? So try to do this, figure out the sine of negative 180 using the unit circle. Yeah, the hint is x, this is y coordinate. The first coordinate is cosine. The second coordinate always sine. That's always true for any angles using the unit circle. Excellent. Anna, yeah, very good, Anna. Well, Anna, well, but you have to think, right? Just look at the coordinates. Look at the coordinates. This is negative 180, right? The clockwise coordinate -1 and 0. They are good. They undefined if you would take tangent or some cotangent perhaps. But here it's defined. Just look at the first coordinate, second coordinate. The first coordinate gives you always sine. The second coordinate always gives you the first coordinate cosine, second coordinate sine, right? Always. All right, let's do it together, guys, so we can move on. We are looking for sine of negative 180 degrees, right? So look in the unit circle at second coordinate, right? Second coordinate. What's the second coordinate here? 0, right? 0. Follow, guys? Right? This guy. Maybe I can do this. Great. Right? Yeah. Very good, very good. So that was the answer for this problem. Now, this unit circle helps you not only to determine cosine and sine, also to find the relationship between sine and cosine, right? For example, long ago, I mentioned identities, right? And I promise you that using the unit circle, we will be able to prove them, to show that they are true. Notice bottom line right here, this is saying that this guy should be always cosine of theta, and this guy will be sine of theta, right? Sine of theta, right? X is cosine, Y is sine. So for example, here in this triangle, then you can see that clearly that sine squared plus cosine squared has to be equal to 1 squared, which is 1, right? There you have the Pythagorean identity. You can take tangent of theta, sine over cosine, right? There you have the quotient identity. Then you can say, for example, cosecant of theta, 1 over sine, right? So all the trigonometric identities can be easily justified using this unit circle, right? Using unit circle is a very powerful tool. Okay, but now let me talk to you about this unit circle, helping us to figure out what to do when we work with negative angles, okay? With negative angles. Let's talk about that down here. Yeah, and then I will show you a sheet that I want you to have. I will show you that. Yeah, first, trigonometric functions of negative angles. Suppose you have a positive angle theta here, and you are working in the unit circle, okay, to help yourself out, right? Alpha here, and you have here same amount of rotation, but clockwise now, negative alpha, negative alpha. How are these two guys related, alpha and negative alpha? Look, since this is 1, the unit circle, draw a perpendicular here, perpendicular here. Notice these two distances have to be the same, right? Because these two triangles, the one on the top, the one on the bottom, are congruent, right? Same triangle. So now we just showed that if you work in the unit circle, then this point has coordinate, which has coordinate x and y, has also coordinates cosine of alpha and sine of alpha, right? So this guy cosine of alpha, comma, sine of alpha. This is x, this is y, right? But now, if you look down here for this angle, cosine of alpha and cosine of minus alpha should be the same because they have the same first coordinate, right? You see it here? They share this, right? So this guy is still cosine of alpha. But when you go up here, when you go to sine, sine is different, right? Because here is positive, here is negative. So this will be minus sine, right? You follow that? The y coordinate is negative here, so minus sine. But look at this relationship, right? Cosine the same, sine here, minus sine here. All right, great. So now then we can write out some properties here, some properties. For example, I can say that sine of negative alpha is equal to negative sine of alpha, right? You follow that? Negative sine of alpha. Cosine of negative alpha, since they share this, both angles, right? The first coordinate is the same as cosine of alpha, right? Cosine of alpha. Cosine of alpha, same as cosine of negative alpha. And tangent, since it's sine over cosine, it will be this guy over this guy will be minus tangent of alpha, right? Minus tangent of alpha. Now, for cosecant, secant, and cotangent, we take the reciprocals of sine, cosine, and tangent, and we can show that cosecant of negative alpha will be minus cosecant of alpha, right? Because remember, when you flip a fraction, the sign stays, right? If the original fraction was positive, when you flip it, you will end up with a positive fraction. If the original fraction was negative, when you flip it, when you take the reciprocal, will end up being negative, right? So this is justified. Cosecant, sorry, of negative alpha is equal to minus cosecant of alpha. Secant of negative alpha will be equal to secant of alpha, because notice cosine of negative alpha is the same as cosine of alpha, right? Cosine doesn't care about the sign of the angle. It's just the same. Now we come back to tangent. Tangent cares, right? So cotangent of minus alpha minus cotangent of alpha. Somehow, something that will remind you about these three facts is this. If you are dealing with sine, you have to take the negative sign outside and put it up front. Cosine doesn't care. It's the same. Tangent cares, so also the negative sign should be placed in front, right? Similarly here. Similarly here. Okay, guys? So this is to go from the negative angle to the positive angle, right? Yeah, great. So let me give you an example here, and we'll go back to the worksheet. Given sine of theta equal 5 over 13 and cosine of theta equal negative 12 over 13, find sine of minus alpha, cosine of minus alpha, and tangent of minus alpha, okay? Let's do this together. So let's start with sine of minus alpha. Sine of minus, in this case, theta, right? Let's be proper, theta. Sine of minus theta. They're asking me for this. Well, I have a property, right, that says that sine of minus theta is equal to minus sine of theta, right? But sine of theta, as I have it, is given here, right? So this will be just equal to minus, put here, 5 over 13, done with this. What about cosine of minus theta? Cosine, remember, doesn't care about the sign of the angle. It's just the same. It's cosine of theta, right? Cosine of theta, the same. But cosine of theta is given. Is this minus 12 over 13. I got sine of minus theta. I got cosine of minus theta. Now I can get tangent of minus theta, right? Tangent of minus theta. But tangent of minus theta, again, tangent minus, so minus tangent of theta, right? Minus tangent of theta. But what is tangent of theta? It's just sine of theta over cosine of theta, right? And that should be just equal to minus here. Sine of theta is 5 over 13. Cosine of theta minus 12 over 13. Minus and minus plus. Notice you flip the fraction on the denominator, and then you multiply that by the fraction on the numerator. 13 cancels. You end up with 5 over 12, right? So that will be tangent of minus theta. Follow, guys? Yeah, great. Now let's do this other example. Example 2, compute sine of negative 420 degrees in exact form. Okay, so we start with sine of minus 420 degrees. Working with negative angles, not so easy. So let's use our property that says the sine of negative 420 degrees is just minus sine of 420 degrees, right? Let's take the sine outside. But now how I deal with this angle? Well, remember the general recipe, right? The general hint, the general advice. When the angle goes over a full round, which is 360 degrees, immediately subtract those unnecessary full rounds, right? I'm gonna subtract 360, and that's gonna be 60 degrees. And instead of working with 420 degrees, work with its coterminal angle, coterminal. Which is 60 degrees, right? Trigonometrically speaking, in the world of trigonometry, 420 degrees, exactly the same as 60 degrees, right? Yeah, trigonometrically speaking, so work with 60 degrees. But what is sine of 60 degrees? Remember I gave you guys this, remember, recall. Sine of 60 degrees is equal to the square root of 3 over 2, right? Yeah, I gave you a table and we did this, right? But now, guys, good news. All these results that I gave in a table, right? In a table, can be gotten from this unit circle sheet that I urge you to have handy to print out. I have put it in our website as usual under useful sheets. It is here. I can give you the link, direct link in the chat. Let me just put it there. So this sheet is going to be extremely important for us. Yeah, so this is going to be extremely important for us. Here is the link, right? Get it from there or print it out. But this is going to give you sine and cosine of all these special angles. You will see how this works. Let's say right now, I want to have or to get sine of 60 degrees, right? Where is it here? Well, you go to 60 degrees. Remember, the first one is always, this guy is always cosine. The second one is always sine, is sine. So I need sine of 60 degrees, right? It is square root of 3 over 2, right? You see, guys? Now, next to 60 degrees on this sheet is the angle in radians, 60 degrees, pi over 3. So this sheet gives you a lot of information, gives you the main angles, 30 degrees, 45 degrees, 60 degrees, and even more angles on the second quadrant, third quadrant, fourth quadrant, but also gives you cosine and sine of those angles, right? The first coordinate cosine, the second coordinate sine, right? I needed sine of 60 degrees. I go to the sheet. I know it's square root of 3 over 2, right? It's there. It's there. You follow, guys? Very good, very good. So have this sheet printed out handy, right? Yeah, great. All right, now let's see how we can use this sheet and how we can use our tool that is given by using the unit circle. And let's go to the worksheet and practice. Okay, for example, can you figure out in the worksheet this question? Cosine of minus 90 degrees, either using the formulas for negative angles or drawing this on the unit circle, right? Try to do this. I will give you a hint. Where is negative 90 degrees? Well, if you draw a unit circle here, right? You go clockwise, negative 90 degrees is there. So pay attention to the coordinates of this point. In the unit circle, since it's 1, 1, 1, and 1, this guy should have coordinates negative 0, comma, negative 1, right? Yeah, good. Remember, the first coordinate gives you cosine, the second coordinate gives you sine, right? Or you can also use the knowledge of negative angles, right? Your formulas. Cosine of 90 degrees should be the same as cosine of negative 90 degrees should be the same as cosine of 90 degrees. So you can use 90 degrees as well, right, for cosine. Yeah, so what should be the answer for this problem? Cosine of 90 degrees. Remember, this is x, this is y coordinate. This is always cosine. This is always sine. Okay, yeah, let's go over this together so we can go over more examples. Okay, from the unit circle, we can say that cosine of negative 90 degrees is equal to, here we look at the first coordinate, 0, right? 0 from here, cosine. Now, alternative, you can say alternative cosine of negative 90 degrees is equal to cosine of 90 degrees by the properties associated to negative angles, right? Cosine doesn't care about the sine of the angle. But this guy can be found from our unit circle sheet because you see here 90 degrees. Look, first coordinate cosine, second coordinate sine. First coordinate cosine of this 90 degrees, 0, right? 0, 0. Very good. This guy, 0. Using unit circle sheet. Very good. Okay, great. So now let's try another one. What about this cotangent of negative 810 degrees? Find it in exact form. Yeah, let me show you this. Okay, so this will help you in your homework. Quickly, since it's difficult to work with negative angles, right? Take the sign outside following the properties of our negative angles, right, that we showed. So this will be equal to this, right? But now 810 is a very big angle, right? Let's subtract 360 as many times as needed so that we can work with an angle within the unit circle within one full revolution, right? When I subtract 360 the first time, I get this 450 degrees. It's still huge, it's still bigger than 360 degrees. So I'm gonna subtract again 360, right? You can subtract these unnecessary rounds as many times as you want. So now, I get that this is just 90 degrees, better, right? 90 degrees. So, and this angle 810 degrees and this angle 90 degrees are coterminal, right? Coterminal. Coterminal angles, so they are trigonometrically speaking the same. So this is cotangent of 90 degrees, right? But cotangent of 90 degrees can be found as cosine of 90 degrees over sine of 90 degrees, right? Following the quotient identity. But what is cosine of 90 degrees? What is sine of 90 degrees? Well, you go to your unit circle sheet, and there you will see that sine of 90 degrees is the second coordinate 1, cosine of 90 degrees 0, right? Sine of 90 degrees, again, 1, second coordinate, cosine of 90 degrees 0. So let's replace it here. Sine of 90 degrees 1, cosine of 90 degrees 0. So 0 over 1 negative here. Doesn't matter. This will end up being just 0, right? 0, guys. Follow? Try to remember this for your homework. Yeah, I think we can do one more. What about this secant of 900 degrees? Secant of 900 degrees. Can you try it quickly? Reduce the angle first, right? Subtract 360 degrees as many times as needed. Reduce it to a coterminal angle, and then from there you can go. And you can use your unit circle sheet, right, to help yourself out. Yeah, okay, since we are running out of time, let's do it together. This angle is much bigger than 360 degrees, so I'm going to subtract 360 first. I get 540. Subtracting again 360, I get yeah, great. 80, which is better, right? These two guys, coterminal. Okay, so trigonometrically speaking, the same. So this will be secant of its coterminal angle 180, right? But what is this? According to the reciprocal identity, this will be 1 over cosine of 180 degrees, right? Well, what is cosine of 180 degrees? Well, look at your unit circle sheet that I just gave you, right? I shared the link, it's in our website. And look for the angle 180, right? 100, where is that? It's here, right? 180, bigger, look here. And look at the first coordinate, because remember in the unit circle, the first coordinate is cosine, the second coordinate is sine. So first coordinate cosine, cosine of 180 degrees, equivalently cosine of pi radians is -1, right? So let's take that. Let's do 1 over this guy -1, final result -1, okay? So this guy, right, for number 8. And let's see if we can do one more. Check. Try this one, guys. Yeah, it's not so difficult to do this. Cosecant of 270. And I will give you this hint. Cosecant of 270 degrees equal 1 over sine of 270 degrees. And to get this guy, go to the unit circle, right? To the unit circle sheet. So using the unit circle sheet. Get this guy and then compute, do the final computation, right? Here. I'm gonna bring up the unit circle there. Yeah. Look at 270 degrees, right? 270 degrees. Should make it bigger. And remember that in the unit circle, right? The first coordinate is always equal to cosine of the angle, and the second coordinate is always equal to sine of the angle, right? Equal to sine of the angle. Yeah, this guy, remember, always cosine, this guy sine, because we're working on the unit circle, right? The sine, cosine, they come for free there by looking at the coordinates, right? All right, so let's go over this together. All right, looking at the unit circle, sine of 270 should be the second coordinate, right? -1, right? -1. Sine of 270 -1. Very good, very good. So take that. -1. So we do 1 over -1, right? 1 over -1. And that is just -1, right? So final answer should be this one for number 4, guys. Okay, very good.